problem that we're going to look at is going to be very similar to problem number 1 on Unit 3, Worksheet 3. This practice problem is going to be slightly different, but the process should be similar. So, for every single question, we first start off by reading the question. A cup of coffee, 140 grams, cools from 75 degrees Celsius down to comfortable room temperature, 20 degrees Celsius. That means that there's going to be two significant figures in that second number. How much energy does it release to the surroundings? Well, the very first thing we always do is we start by identifying if it's a heating or cooling curve. This worksheet says it's a warming or cooling curve, but overall it's going to be very, very similar. So, what I always like to do is I like to start off by drawing my heating or cooling curve. So I start by drawing a blank curve over on the left, and then I read through the question and look for any keywords that will help me identify if this is going to increase or decrease, the warming or cooling. Well, a cup of coffee cools. Hey, the word cools kind of will tell me it's going to be a cooling curve. Other words that are going to help me out, hey, it goes from 75 degrees Celsius down to comfortable room temperature. So if our temperature is decreasing, that also means it should be cooling down. That's one of the processes we see on a cooling curve. Oh, and then finally, how much energy does it release to the surroundings? Well, release means that we are having our energy get removed from our system. E minus, energy leaving our system. That's what we saw on our cooling curve. So that's going to go on our x-axis. On our y-axis is going to be our temperature. At this point, I'm going to just draw the region of our cooling curve that is going to be addressed in this question. So in this problem, we have our starting temperature, 75 degrees, and it will end up at that 20 degrees. So it should look something like that, where we're cooling down from a higher temperature to a lower temperature. At this point, that's going to be this very first part. For each of the problems, sketch a warming or cooling curve to help you decide which equations to use to solve the problem. Hey, we did that first part. Now what I'm going to do is I'm going to identify the numbers and units that the question gives me and see how it can help me solve this problem. So what I like to do is I like to use that table we set up in our notes, where our notes we started off by identifying the energy. Energy we represented with the letter Q, and the unit was going to be in joules. So, let's see. Ooh, it's not telling us our joules anywhere in the question, and it's asking us how much energy does it release to the surroundings. So we're going to be looking for our energy. Next thing we had in our table of variables was our mass. Our mass we had with the letter M, and that had the unit of grams. So a cup of coffee at 140 grams. I'm going to write that down, 140 grams. Let's see, what else do we know? Well, next thing up on our table was going to be that change in temperature. How our temperature was changing from where we started off at to where we ended up at. Well, it looks like we went from 75 degrees Celsius down to 20 degrees Celsius. It looks like, if my math is correct, that means our change in temperature was minus 55 degrees Celsius, which can go right up there, minus 55 degrees Celsius. Now, those three things we're going to be looking for in every single problem: the energy, the mass, and if there is a change of temperature, and if there is, what is it? At this point, we'll need to go and look at the information at the top of our page in our energy constants. We need to see if it's going to be a heat of fusion, melting or freezing, a heat of vaporization, evaporating or condensing, or if it's going to be a heat capacity problem, which involves a change in temperature. Well, this problem, we drew a cooling curve, and it was cooling from a higher temperature to a lower one. That means we have a change in temperature. That means we get to use the heat capacity. Now, this is going to be a cup of coffee, which I know is going to be mostly water. So I'm going to be using the heat capacity of liquid water, this one up here, for our heat capacity of liquid water. I'm going to write that down here. There are two ways where we can write this. We can write it either with our 4.18 joules of energy up on top is the energy required to change 1 gram of water by 1 degree Celsius. The other way that we can write this problem is by saying 1 gram of water changing by 1 degree Celsius requires 4.18 joules of energy. Now, once we have all of these variables identified, and we'll be using these every single time, our energy, mass, change in temperature, and either our heat capacity, heat of fusion, or heat of vaporization. Once we have that information, we're going to set up a table. Now, for this problem, we're going to be looking for our energy for our final answer, and we know energy is going to have a unit of joules. So I'm going to look at the other variables we know and see if we can convert to joules in some way, shape, or form. So mass, 140 G. G, not J. That's not going to help us out. Change in temperature, minus 55 degrees C. Once again, that's not going to get us to our joules right there. But for our heat capacity, we have our joules up on top or our joules on the bottom. So either of these is going to be an acceptable way for us to end up with joules in our final answer. I'm going to use the one where we end up with joules up on top. So it's going to be this one over here. So what I'm going to end up doing is I'm going to be setting up my ladder over here on the right. I'm going to fill it in with the information I know. I'm going to start off with that heat capacity, the bottom of the ladder, with the orientation I've identified. So 4.18 joules of energy are required to change 1 gram by 1 degree Celsius. But this is the amount of energy if we only have 1 gram of water, or in this case, coffee. But here, we actually ended up with 140 grams. So it should be 140 times bigger, which is why I'm going to put that energy up on top. Well, the mass up on top to get that higher energy. Also, by putting 140 grams on top, that allows me to cancel out my units. Now, one other thing, even though it doesn't tell us we only have 1 cup of coffee, I'm still going to put that 1 on the bottom to say we have 1 of these 140 grams of our substance. Also, this is going to be a nice way to keep a placeholder so we don't accidentally multiply by 0 if we left it blank. So right now we should have a bigger number, which makes sense because we have that energy for every 1 gram. It should be 140 times bigger because we have 140 times more mass than required in our heat capacity problem. Now the other thing we need to do is to get rid of that degree Celsius on the bottom. And that's the amount of energy required to change your substance by 1 degree Celsius. But we're changing this by 55 degrees Celsius. And it's going to get 55 degrees Celsius, that change, well, less. So it's going to be multiplied by 55, and that's still going to allow us to cancel out our units. And we're only having that temperature change once. So my placeholder 1 on the bottom. Now, once I have the information and I've crossed off the units that I don't need, the only unit we need and we can see is joules. Well, that's the unit we're going to be looking for at the very end. So at this point, I know I'm done with my setup. So I'm doing my 2 lines to say I'm done putting in information. Now all I need to do is to plug this into a calculator to calculate how much my answer will be. What I'm going to do is I'm going to multiply the top. My 4.18 times my 140 times my negative 55. Now, one thing I will need to be careful about is when you plug this into a calculator, not to just, well, subtract that 55. I almost did that when I plugged it into my calculator. Just going to do it twice just to make sure that I have my correct final answer. So up on top, I have 32,186. 186 joules. Now on the bottom I have this 1 times 1 times 1 times 1, so I end up with 1 on the bottom. If I wanted to, I could just carry on a little bit further and then write 32,186 joules by dividing the top by the bottom. And that's going to give us our final answer of 32,186 joules. So I'm going to say, oh, and that's going to be negative because we are multiplying by a negative number. So what I'm going to say is that 32,186 joules of energy were released.